Well, all right, everybody. It is 4 o'clock from what I can see on my computer here. Welcome, everybody, to our first class after spring break. First things first, I just want to test real quick. Can everybody hear my voice out there? Give me a thumbs up or by the way, I'm also checking my chat so I can also see it there. All right, sweet. And then the second question, can everybody sort of read what's on this board behind me here? Is it clear enough to be able to read? Yep, so far so good at least. I can always pull it a little bit closer in if we need to, just to make sure that it's, whoops, I'm going the wrong way with that. Just make sure that it's really clear. All right, well, guys, this is not what I had planned. I'm back here at my parents' house. I don't know if I told you at the start of the semester, my parents had some surgeries late last year. They're both turning 80 years old this year, so they're getting up there, and turns out that they've been having some mobility issues and some challenges. They still have a pretty big house over here that they had even in their younger years. And so they sort of have had some issues they needed me to help out with this week. And so I really didn't want to leave them hanging since they've done a lot for me as well in my life. So I decided that if you guys could be patient enough with me to allow me to just teach this week over here, I can help my parents out quite a bit. I am going to be coming back next weekend, and so we'll be back in person next Tuesday. And in fact, I'll be back on campus by Monday next week. But we're going to do this week everything in Zoom. So tonight's class, Thursday's class, as well as all of the office hours this week in Zoom. And I hope that things will go pretty smoothly to do it that way. It should be fine. But I hope that you guys had a good spring break, got a nice chance to relax a little bit and rest. We were working pretty hard in March to really get on top of things, and I think we're in a really good position now to be able to do well with finishing up the semester strong. I'll make a couple of announcements here. There is a homework assignment due tonight. And my plan is to save some time to answer questions from that assignment, although I have to tell you, I did not think I was going to be here this week, so I did not bring my book with me. I think I have some of the homework problems in another, I can pull up something that has the homework in it, so if we have questions on that, I should be able to find those problems. So I'll take some questions a little bit later in the class today. I just wanted to also remind you guys on some of the true false homework problems, you are supposed to give at least a brief reason. It doesn't have to be a long thing that you write out. It doesn't have to be a whole page or anything like that, but at least a line or two. Why is the statement true or why is it false? Maybe you give a counterexample or just some brief little justification if it is true. Those things are very helpful. So please try to do that. If you need help with the true false items, we can also talk about that today as well. So feel free to do that. Anyway, so after my second class, which is my usual schedule at 8 p.m., I will be going into Zoom for my office hours. So if we don't get a chance to answer all of your questions during tonight's live Zoom session, you certainly can come by in my office hours later on this evening. So that's the homework for tonight. There is also an assignment that will be due on Friday, and we'll be covering the material related to that material today. And if you've got questions on that, I'll take those on Thursday. Okay, so kind of doing the usual routine. We're just doing it all through Zoom this week. It's not I don't like it because I don't have as much board space, but I think I can make this work. We did it once before, so we're gonna try to make it work again. Does anybody have any questions out there about kind of logistics or kind of where we're at with the assignments and the schedule for this week, or is it all pretty clear? I'll pause for just a second in case anybody wants to ask me about that, and then we'll jump into the math here tonight. And I do have my chat window open. If you're in a situation where you want to ask me, and I understand technology is not perfect, so if you feel like you're speaking over me or something, don't worry about that. I totally get it. It's not really a perfect setup, but we're gonna make this work. I'm actually, if I had to pick something that I could cover in Zoom, this would probably be it. This is sort of bread and butter material that I think we can explain it. I'm going to try my best to explain this topic, as clearly as I can. If you remember, we are starting chapter 7. And on that last class before spring break, which was 12 days ago now, I had started talking about eigenvalues and eigenvectors a little bit. So the plan for tonight is to really dive into it now. And I'm going to kind of start mostly from the beginning. I won't rederive everything that we did last class, but I'm going to try to, of course, do my usual recap and then really dive into this tonight in quite a bit more detail. As I mentioned before, this is a really, really important topic in linear algebra. It has applications to statistics. It has applications to computer science and computer graphics. Eigenvalues and eigenvectors are also going to be pivotal to our ability to solve systems of differential equations, which we are actually going to do in this class in just a couple weeks from now. So we're rapidly getting to the point where we're finally going to be able to use all of this material that we've been learning for the last several weeks, the linear algebra that I know has been dragging on for several chapters now. We are kind of at the end of the linear algebra diversion, and we'll soon be going back to differential equations. Okay, so with that sort of as the framework, I'm gonna stand up now, and I'm gonna remind you kind of where we left off on the week before spring break. We're talking about eigenvalues and eigenvectors, and you can see here that the matrices are always square size. So A is going to be an n by n matrix, and in that case, we can talk about eigenvalues and eigenvectors. I usually like to use lambda. This is the Greek letter lambda for the eigenvalues. Those are just numbers. Those are just scalars. So lambda is an eigenvalue, and there's always going to be a corresponding eigenvector. And I will use V for the eigenvector, and this will be a vector in Rn. Okay, so we're not working with any bizarre vector spaces here. We're always working with real numbers, and we're working in Rn when we identify the eigenvectors. Over on the other board here on the other side, guys, I've written down the most important equation in chapter 7. You might remember I referred to it that way before spring break. Here it is. The eigenvalue-eigenvector relationship is expressed as this equation. A times V, so remember this is a n by n matrix, times a vector which is expressed as a column. A times V equals lambda times V, right? And I've drawn this picture here that you can see on the top right side. If you start with your vector V, then it will be an eigenvector if A times V, this is a multiplication here, A times V is simply a stretched scalar multiple of V itself. And that scalar multiple is the lambda value. That is the stretch factor. And here I've drawn the picture to show that the A times V really is stretched. But I've mentioned before that the lambda could be a negative number, which would literally turn the vector around, right? It could be pointing in the opposite direction like that. Or lambda could be some fraction that's between 0 and 1, and that would not be stretching the vector so much as it would be shrinking the vector or compressing the vector. So that's another possible scenario as well. Okay, so we have this idea of eigenvalues and eigenvectors. The most important equation in chapter 7 should always kind of be in our minds. It's certainly very important. And it's actually relevant for some of the homework for tonight from section 7.1. So if we've got questions about how to use that, certainly we can do that later. Before spring break, I talked about how to find the eigenvalues and eigenvectors of a matrix. And I've got two boxes here that kind of express the summary of how that works. The eigenvalues, these are the lambda values, just come from the solutions to this characteristic equation. So I derived all of this before spring break. I'm just reminding you here that we have to take this determinant. Of course, we have an n by n problem, and so the matrix is a square size, and we can take that determinant. Notice that you have to subtract lambda times I. That I is the identity matrix. So you're going to be subtracting lambda off of the main diagonal of A, and we set this determinant equal to 0. This gives us an equation. It's called the characteristic equation, and that equation has solutions which are the eigenvalues, right? So the solutions to that characteristic equation, they give us the eigenvalues of our matrix, right? And so we're going to practice solving this characteristic equation tonight. I'm going to do at least 3 or 4 examples of this. We did one example before spring break, but I'm going to come back tonight and do 3 or 4 more. So usually the first step, guys, is to find the eigenvalues of the matrix. Right, so we do that first, and then for each of the eigenvalues that we find, we then have to find the corresponding eigenvectors. And those are the v vectors. Remember that an eigenvector should be not 0. And those eigenvectors are simply the vectors that are in this null space of A minus lambda I. Okay, so by now I'm hoping that null spaces are pretty familiar. We've been doing these really for 3 or 4 chapters now. We actually have to calculate a lot of null spaces. You're going to see null spaces left and right on my board tonight. We're going to calculate lots of null spaces. These particular null spaces are called eigenspaces because they are associated with eigenvalues and eigenvectors. So these are eigenspaces corresponding to lambda. And I will often denote the eigenspaces as E sub lambda. And so the eigenvectors are simply going to be the vectors that are in that null space. So if you don't know how to find null spaces, this chapter is not going to go very well. If you don't know how to find determinants, this chapter is not going to go very well, right? That you can see that those are the crux calculations that are involved in finding eigenvalues and eigenvectors. I'm not worried. I know you guys know how to do determinants and null spaces. I've been hammering that over you for several weeks now. So I'm hoping that that will be good. In fact, if anything, it'll be a nice review. It'll reinforce and keep us fresh on how to do determinants, how to find null spaces. And in that sense, this should be a good thing, actually. Are there any questions so far? This is just, we didn't get that far into it before spring break. I just wanted to kind of get the highlights on my board here. The main thing we're going to do, though, is we're going to warm up here and we're going to do some practice problems. So are there any questions before I do that? And I'm still looking at my chat window. I can still hear you if you want to use your microphone. If there's anything that's not clear, speak up anytime. Okay, maybe we're doing so far so good. So I'm going to step back around to the other side of my board again here. And I'm also going to turn on the heater in this room. I told my parents I'll be here to help you guys out if you need it, but I might be running up your heating bill. Because I don't know if did I tell you about when I tried to teach out in my garage in Colorado during the pandemic? and it was the middle of winter, everything works fine. I mean, I don't mind. I can dress up like an Eskimo and be cold, but the whiteboard doesn't erase. I didn't know this, but if it's really cold in the room, the whiteboard will not erase. And so I have to turn heat on to kind of keep this board erasing well. So anyway, I'm going to turn on my heater for a second. But yeah, let's practice on this little 2x2 example that I have here, guys. So this would be a typical problem that you would have. It just asks us to find bases for the eigenspaces of this matrix A right here. So -1 and 6 on the first row and 9 and 2 on the second row. And these are null spaces after all, so they will have bases, right? These are actually subspaces of Rn. And so we will expect these to have bases. Okay, so let's try it, guys. Let's see if we can shake off the dust from the spring break that we had and get back into it here. For the solution, remember the first thing we want to do is find the eigenvalues. So I'm going to start by finding the characteristic equation. That's what this first box tells us to do. So we're going to take the determinant of, now what matrix is it? It's the matrix A minus lambda I. That means I'm going to subtract lambda from the diagonal entries of A. So we only subtract lambda from the diagonal entries of this 2x2 matrix. And so this is what the matrix will look like. Again, why is it the diagonal entries? It's just because the identity matrix has ones on the main diagonal, right? Zeros everywhere else. So I'm not subtracting anything from the 6 or the 9, only from the diagonal entries. This is just a 2x2 determinant. So as long as the spring break wasn't too long, we hopefully remember how to do the 2x2 determinant here, right? So this is going to be equal to -1 minus lambda times 2 minus lambda, and then minus 9 times 6, which is actually 54. And this is a little quadratic equation. If we just multiply it all the way out to begin with, I think that's a good thing to do first. If I just expand it out, I see that there's a lambda squared minus lambda and minus 56. And remember, the guys, that what we're going to ultimately be doing is setting this characteristic equation equal to 0. You see it up here in the box at the top. We're going to set those equal to 0. And in this case, the quadratic equation factors nicely. Okay, now I'm just going to warn you, this characteristic equation is not always going to factor nicely. In fact, we're going to see it tonight, even on an example I'm going to do a little later, that it does not always factor nicely, but this one does. I'm going to see if I can just write it out for you here. This should factor as lambda minus 8 times lambda plus 7. Okay, and if I am willing to believe that I did all of that correctly, then we can come over here. I'm going to erase this original equation so I have a little more room. If I've done that correctly, then guys, what I can do is write down my 2 eigenvalues. So I have lambda equals 8 here. And let's see if I can actually, it's a small board, but I'm going to try to do both eigenvalues on this 2-column format over here. So I've got my lambda values, which are 8 and -7. Okay? Next step is to find the corresponding eigenvectors, right? So to do those, I have to calculate these null spaces. So let's take a look at the null space on the lambda equals 8 case. Again, what matrix is it that we're taking the null space of? It's the matrix A minus lambda I. Well, right now, lambda is 8. So what we're going to do is we're going to take our matrix A from over here, and we're going to subtract 8 from the main diagonal of it. So -9 and 6, and then 9 and -6. Okay? Now, one little gut check we can do with ourselves on this is the matrix we have here should be not invertible. remember that the determinant of this matrix is equal to 0. That means this matrix should not be invertible. And in the case of a 2 by 2, if the matrix is a 2 by 2, that should really just mean that these two rows should be multiples of each other. Okay, is everybody still hearing me and seeing me okay? If I'm going too fast, just let me know. I appreciate all the feedback. I'm seeing some thumbs up and some nodding out there. This is the null space we need to calculate. Okay, now guys, the two rows, they are multiples of each other. Of course, I'm going to do EROs, but in doing EROs, I'm going to cross off that second row. I can obviously see that I have a pivot right here, essentially. And in fact, I'm going to write down the equation here. Negative 9x plus 6y equals 0. So that's just the equation that would be associated with the first row of the matrix. And as you know, we can just set y equal to t. And if we do that, we can solve for x, which in this case would be 2/3 of t. So if you let y equal t and then solve for x in that one equation that we have, x is going to be 2/3 of t. And so now I can bust out my t and write down my basis. Let's write it this way, guys. The basis for e sub lambda equals 8. This is an equal sign. And what is it? I'll just put a colon here. I'm going to use my braces. And I'm going to bust out the t on both the x and the y. And you can see that I have a 2/3 and a 1. All right. Now, are you guys ready for something new tonight? So far, this is kind of just review. I'm going to show you something new, if you don't mind. And this is the best time to do it. Let's just extend this column a little further. But this is an important thing. And I didn't used to teach this, I'll be honest with you. When I was first kind of a new professor, I didn't realize how handy this little trick is. But I'm going to show you something that I'm going to call the A-B trick. Now, this is not in the book. This is something that after teaching the class about 40 times, I've kind of figured out that this is a handy thing for students to be able to use. And what that is the following thing. When you're doing a null space, and when you have just two numbers in this row, so you see that? See this row right here? This is going to be the A, and this is going to be the B, right? And you have this equation, AX plus BY equals 0. Do you see that? In this problem, it was negative 9x plus 6y equals 0. It's kind of what I'm talking about. The A and the B are just these two numbers, negative 9 and 6. Then there's actually a way of getting your eigenvector without having to set up these free variables like this. And what it is you probably have noticed that if you just let x be equal to negative b, and you let y be equal to a, this is the A-B trick. The A-B trick is that if you let x equal negative b, and if you let y equal a, you get a valid solution to this equation, right? You can check it. A times negative b plus b times a does equal 0. It does work, right? And so your eigenvector is negative b and a. Let's write that down. So the eigenvector becomes the x value of negative b and the y value of a. All right, guys, within the sound of my voice, are you following this? This is not really explained specifically in the book. Let me just slow down for a second. What I'm explaining right here is kind of optional. There's nothing wrong with what we did at the top, right? There's nothing wrong with all this work we did. What I'm trying to do here is save you a little effort. I'm saving you a little effort because what I'm basically saying is when you have a little 2x2 system like this, and you have one equation that has the form ax plus by equals 0, and you're trying to come up with an eigenvector, which we're going to be doing 100 times in the next 2 weeks, right? You can get it by simply taking the two numbers A and B and doing, what are we doing here? We're swapping them. We're putting the B first and the A second, and we're putting a sign change on, in this case, the B. It turns out we could have let x equal B and y equal negative A, and that also would have worked. So guys, I'm going to give you basically another basis. Let's see if I have enough room here. Basis for E sub lambda equals 8. I want to come back to my example again. And instead of doing the free variables here, I'm going to put the negative of B and then the negative of A. Sorry, the negative of B and then A itself. So that would be -6 and -9. Take a look at the basis we came up with here. 2/3 and 1. Down here, the basis we came up with was -6 and -9. Does anybody have a problem that we had two different bases? Does that bother anybody? Guys, they're both correct. This one is just a multiple of this one, right? Remember, when you're finding a basis for a vector space, there are lots of correct answers. And if you have one correct answer and you just scale up the entries by a constant, if you just do a scalar multiplication, you get another correct answer. In fact, I could make another correct answer. In fact, I'm going to make another correct answer. Where do I want to do this? Maybe I'll go over to the other side again. Fook, I saw your question. I'm going to answer it in just a second. But let me come over here. I'm going to write down another correct answer, because some of you might be looking at that thinking, I don't really want to have negatives in my basis, right? So another basis, let's just put it right here. Another basis for E sub lambda equals 8. We could just get rid of those minus signs and just use 6 and 9. Nothing wrong with that either. So if you don't like the minus signs, just get rid of them, 6 and 9. So are you guys with me on this? This is just a trick. This is not like, oh, we have to use this. This is just an easy way. I probably could have showed you this a month ago, to be honest. When we have a 2x2, this is what Fook is saying in the chat. He's saying, would this work for any matrix, or is it just for 2x2? When we have a 2x2 matrix and we have just a single equation with one set of values, A and B, across one row, we can eyeball it. That's what I'm saying. We can eyeball the solution by just swapping the A and the B. So switch the positions, in this case, switching the positions of the -9 and the 6. So I put the 6 first and the -9 second, but then I have to do a sign change on one of them. So we could have, over here, let's just add this. We could have done B negative A. That's also fine. I would actually suggest you write that down. It could be negative B and A, or it could be B and negative. These are just multiples of each other. They're both equally correct. Okay? Oh, I hate not being in the classroom with you guys. That's when I can like look you all in the eyes and make sure, do you get this? Do you understand? I hope it's clear. Guys, it may seem unnecessary. It is unnecessary because the basis that we came up with here would have been just fine. However, later on tonight, you're going to see some examples where you're really going to enjoy having this A-B trick. It may not seem like it would be a big deal. It's not so hard to bring in the free variables here and just bust out the T. But you're going to see soon that there are cases where it is a big deal. So keep this trick in mind. This is one of the big things I wanted to explain in the first part of our class tonight. Now, Fook, to answer your question, and I really appreciate your question. To answer your question, let's say I had a 3x3 matrix. In that case, there is no A-B trick. However, I always have an afterthought here. if one of those three variables has already been solved for. So in a 3x3 system, if I've already figured out what, let's say what z is. So maybe we have an x, a y, and a z on a 3x3 system. If I've already figured out what the z variable is, I can play this A-B trick on the remaining two variables. I can't do it sort of from the top get-go, but once I've gotten rid of one of my unknowns and I only have two unknowns that I'm trying to solve for, I can play this same game, and it's really, really handy. So yeah, we are going to use this trick not just on 2x2s. We are going to see situations where it helps us solve 3x3 systems as well. So great question. I hope, does that make sense? Until you actually see an example, it maybe isn't totally clear how that works, but we are going to see examples, and then I'll show that to you. Let's go to the other eigenvalue. I've left some space over here. We've got another lambda value to play with, -7. So there's going to be a null space here as well. Let me write it down. Null space of, and now I want to look at the matrix that I get when I add 7. So here's the original matrix A. I'm going to add 7 to the main diagonal of this matrix. So 6 and 6 and 9 and 9. Okay? Again, this matrix is not invertible. The two rows are multiples of each other. I can cross one of them off. I'll do that. I can actually go ahead right away and use my A-B switch trick if I want to. So basis for E sub lambda equals -7. Let's try and do it, guys, without even introducing free variables. Let's see if we can do it. Okay, so here's my trick. My trick, and this one's easy because the A and the B are the same. Right? The A and the B are both equal to 6. What's my trick tell me to do? Oh, it tells me to swap the A and the B and put a minus sign on one of them, whichever one I want. So I could do a -6 and 6. Does everybody see how I got that without showing any work at all? I just literally look at these two numbers, I swap them, which in this case doesn't amount to anything, and then I do a sign change on one of them, either the B or the A. You can do either one of those. Okay? That's kind of how that works. Okay, I'm hoping that that makes sense. Are there any questions on this example? We've finished the example. The example is asking us to find bases for the eigenspaces of this matrix, and I have done it. I have done it. Okay, let me get some of this out of the way. You guys can imagine all the hell that breaks loose if you get the eigenvalues wrong, right? For one thing, if you get the eigenvalues wrong, then when you do these null spaces over here, you're not going to get any free variables. And so if you're not getting any free variables, then there won't be anything to bust out, and you'll be like, well, then how do I get a basis, right? So if you don't have the eigenvalues correct, you really are going to have a hard time. One way to test yourself is that when you write down those null space matrices up there, you should observe that a row can be crossed off, right? You should not have pivots going all the way down the diagonal. If that were to happen, you'd have no free variables, and it would not be consistent with the theory, which is that those matrices are not invertible. So make sure that when you write down the null space matrix, that those matrices are not invertible. That if you did even if you don't do the EROs, you should be able to convince yourself that if you did the EROs, there would be a row of zeros. There would be a row that you could basically cross off. When I'm crossing off a row there in these null space matrices, what I'm really doing is I'm saying, you know what? I don't want to do the EROs, but I know that if I did them, I'd get a row of zeros, which we can basically ignore. That's essentially what I'm doing over here. just to save a little bit of time. So one way to make sure that your lambdas are correct is to look at the matrices that come up when you start working out these null spaces. But there is another thing that you can do as well. And I'm going to put that here as something I like to call the fun facts about eigenvalues. These are some fun facts about eigenvalues. I've got 2 of them for you. I mentioned them briefly 12 days ago, but I didn't write them down. And tonight I want to write them down. The first one is that if you add up all of the lambdas, if you add them all up, lambda 1 plus lambda 2 plus lambda 3, if you add them all up, you should get the so-called trace of the matrix. The trace of the matrix. Does anybody remember what the trace was? The trace of a matrix? It's just what you get when you add up the main diagonal. Edgar, thank you. Yes, that's exactly right. If you add up the main diagonal values, that's the trace. Take a look at our example here. If you add up the diagonal values of this matrix A, negative 1 plus 2, that adds up to 1. And look at the lambdas that we came up with, 8 and negative 7. Those 2 lambdas add up to 1. So that checks, right? That's a check. So this is a way to check that you have the lambdas correct. If you add them up, it should agree with the trace of the original matrix. Very, very easy fun fact to apply. And then there's a second fun fact that is a sort of a double check, sort of a second level check, which is if you multiply the lambdas, lambda 1 times lambda 2 times lambda 3, you should get the determinant of the matrix. And if you look at the determinant of this little 2x2 example that we did, negative 2 minus 54 is negative 56. Negative 56, yep, if I multiply 8 times negative 7, I get negative 56. Okay, so that does make some sense. These fun facts are generally proved in Math 307. It's a more theoretical thing. I'm not going to do it right now in this class, but I do suggest that you get these fun facts memorized ASAP. They are super helpful just for confirming that you have your lambdas correct. Right, and I think that's very important. Okay, I'd like to do some more examples of this, but before I do, are there any questions so far? 2x2 matrices are pretty easy. It gets a little more interesting when we go up to 3x3. So I'm going to practice a couple more examples with you here. So let's go to another example. Where is it? Yeah, okay, so let's go to example. I don't know, did I number that first example as example 1? If the warm-up problem isn't numbered, you might want to label it as example 1 because this is going to be example 2. It's the same question. Find bases for the eigenspaces of, just so we don't confuse it with the first example, I'll call the matrix B this time. And this time I'm going to go up to a 3x3. So 2, negative 5, and 5. 0, 3, and negative 1. And 0, negative 1, and 3. Something like that. So we're going to do the exact same thing that we did on the last problem, but now we have a 3x3. And I'm going to point out some of the differences that come up when the matrix is 3x3. The first thing is, for the solution, we're going to start off by trying to find the characteristic equation. So that means I need to subtract lambda off of the main diagonal of the matrix. So you're going to see me do that. I'm just going to subtract lambda off of all of the main diagonal values. Now, back in the determinants chapter, chapter 3, We talked about different methods for doing determinants. For a 3x3, one of the things we learned was a so-called arrow method. You remember that? You sort of make some arrows through this little matrix, and then you end up with some terms to write down. It turns out, guys, that the arrow method is not so good in this chapter. It's not so good. The reason is that if you start looking at this arrow method, so don't write this down. I just want to show you, if I do the first arrow would be something like this, right? 2 minus lambda times 3 minus lambda times 3 minus lambda. And then we'd have plus something, minus something, minus something, minus something, right? In the 2x2 example that I did a few minutes ago, we only ended up with a quadratic equation. And I don't sweat too much over quadratic equations because I know I can factor them. We have the quadratic formula. We can always find the roots. But if I was to multiply this thing out, I would not get a quadratic equation at all. In fact, I would get lambda, 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 right? There would be a lambda cubed showing up in this characteristic equation. It would be a cubic equation. And unlike quadratics, which I feel really good about finding the roots of, I don't feel so good about finding the roots, at least not by hand. I don't feel so good about finding the roots of a cubic equation. And unfortunately, if we use the arrow method, we're going to be stuck in that pickle. We're going to have to solve a cubic equation. It turns out, though, that sometimes there's a way out. You have to kind of trust whoever's writing the question to make it a reasonable problem. But does somebody notice something about this matrix as far as, like, other than using the arrow method, is there anything nice about this matrix that might suggest another way to do it that would be maybe better in the long run? Yeah, we've got, okay, you guys are right all over it in the chat there. If we look at the first column, there are a couple of zeros here. And if we do cofactor expansion, that's what Anthony's suggesting. If we do cofactor expansion along the first column, watch what happens. I'm going to do that. I'm going to expand the first column here. I'm going to expand the first column. If I do that, I have 2 minus lambda times, and then remember how we do this? We cross off that row and column, and then we write down the little 2x2 that's in the other corner of the matrix. So it would be 3 minus lambda times 3 minus lambda minus -1 times -1, which means -1. This is what we have. And there's nothing else to it because the rest of the cofactor expansion is just zeros. I have 0 here and I have 0 here. So this is it. This is the whole thing. Now, guys, this is still a cubic equation. I'm not saying that somehow we have avoided a cubic equation. This one is a cubic equation. But you know what I like about this that would not have been so nice with an arrow method approach? What I like about this is it's already partially factored. This 2 minus lambda has already been factored out into the front, so I don't have to worry about anything to do with that. In fact, I'm going to leave that alone out in front because it's already factored out. Guys, I want to get it factored, don't I? That's how I'm going to get my roots. That's how I'm going to solve for lambda. I'm going to get this thing factored. So this is great. The 2 minus lambda is already factored out. Now, the part in brackets isn't looking quite so nice. However, the part that's just in the brackets, in and of itself, is only a quadratic equation. If I just look in these brackets, I have a quadratic equation. Imagine foiling it out. If I foiled that out, I would get lambda squared minus 6 lambda plus 9 minus 1 is really plus 8. And so there you go. This is a quadratic equation, and that can be further factored. So if I factor that, I'm just gonna do it by inspection, guys. It just factors as lambda minus 2 times lambda minus 4. So that's the factorization right there. Okay, so let me come over to my other board here, and I'm going to try now to write down my lambda values. Get this cleared off. Hopefully this is mostly getting through. I know it's not ideal, but hopefully you guys are following it okay. I am keeping my eyes on the chat though, so if there's anything you want to ask me, you can use that or your microphone as we go along here. But if I set this equal to 0, if I set that thing equal to 0, guys, I see that my lambdas are 2, 2, and 4. Now, I want to point out something very important here as well, guys. I always choose my examples to try to show you as much as I can out of them. What I want you to notice is that one of the lambdas was repeated twice. When the eigenvalues repeat like this, you're going to want to keep track of that. So I'm going to suggest that when you see the same, see, because we have lambda minus 2 minus lambda and lambda minus 2, they both give you the same lambda value. If that lambda value occurs twice as a root of this characteristic equation, I want to write it down twice when I'm listing my lambdas. And in fact, when I'm doing my fun facts to check my lambdas, I need to keep track of those repeats there as well. If you look at the trace of this matrix, let's do the fun facts. Let's just check and make sure these lambdas are good. If I do the trace of this matrix, I've got 2 plus 3 plus 3, that's 8. And if I add up these lambdas, it adds up to 8. Now, if I didn't write down the repeats, it would not have added up to 8. So make sure that you include these repeats when you're applying these fun facts and writing them down. I'll let you guys check the determinant of this matrix. Turns out it is equal to 16. And if you multiply these lambdas together, you get 16. So the fun facts check, that gives me, that's not a guarantee that your eigenvalues are correct, but it sure gives me some reassurance that they are probably correct. Okay? So guys, we have 2 eigenspaces here that we have to work on. For reasons that we're going to see later today, if you have a repeated eigenvalue, it's generally better to start with that one. So in this case, lambda equals 2 was a repeat, and so I'm going to start with that one. I'm going to do a null space here. And how this works, remember that what we have to do is subtract 2 off of the main diagonal of my original matrix. So if I subtract 2 from all of the main diagonal entries, I'll get the first row is 0, -5, and 5. 0, 1, and -1, and 0, -1, and 1. Okay? That should be the matrix. Remember, this matrix should be not invertible. And in fact, do you guys notice something here? All 3 of these rows are multiples of each other. They are all multiples of each other. I can cross off 2 of them because 2 of them will actually get zeroed out. I only have 1 pivot that's going to make it to the end of this calculation. I'll circle it there in the middle. My unknowns are x, y, and z. And what we can see is that z, I'm not going to use this AB trick here because we're not looking at a 2 by 2 matrix. So for right now, let's just ignore that. But I see that both x and z are free. So I'll call z equal to t and x equal to r. And then in the middle, I have to figure out what y is. I can do that in my head. I see that y minus z from the middle equation here, guys, in this matrix. Y minus z should be 0. Y minus z should be 0, and that just means that y equals z. So you just get r for x, y, t for y, and t for z. Okay, and guys, now what I do, as usual, if I put that into a vector, r, t, and t, right? then I'm just gonna bust out my variables to get my basis. So let's go ahead and write it down. The basis for this eigenspace, this is the eigenspace corresponding to lambda equals 2. When I bust out the r, I'm going to get 1, 0, 0. And when I bust out the t, I'm going to get 0, 1, 1. So that would be the answer for the basis for the first eigenspace. Okay? So far, so good? If I'm going too fast, just let me know. Okay, let's look at the other eigenvalue. The other eigenvalue is lambda equals 4. All right, so for lambda equals 4, we have another null space we have to calculate. I told you, you guys are going to get really good at null spaces. If you aren't already, you're going to be really good at these because they come up constantly in this chapter. So this time I'm going to subtract 4 from the main diagonal of the original matrix B over there. So -2, -5, 5, 0, -1, -1, and 0, -1, -1. Something like that. Remember, this matrix cannot be invertible. So I've subtracted 4 from the main diagonal of B. Everything else, I left it exactly the same. But you can see that the third row is just a repeat of the second row. I'll go ahead and cross that off. This time I actually do have 2 pivots. There are 2 positions that will be pivots. I'll go ahead and put diamonds around those now so you can identify them easily. And so the only free variable this time would be z. So I'll just let z be equal to t. And then if I just look at the second row here, does everybody see this? If I just look at the second row, I have basically y plus z equals 0. The y and the z, it's really -y minus z. I can think of that as y plus z equals 0. So y will be equal to -t. And from there, you actually do have to figure out what x is using the first equation. I'm going to just save you a little bit of misery on that. And I'm just going to tell you that the x will turn out to be -5t. So you can check me on that. Oh, and there's a blind spot here on my board because of the there's a little bit of a glare. That just says -5t. Let me just put it here. X is -5t. Okay, if I now bust out my variable, I'll get my basis. So I'll bust out my variable here. I'll get my basis for the eigenspace E sub lambda equals 4. And my basis here, if I bust out the t, I'll be left with a -5, a -1, and a 1. And so this would be my other eigenspace. Okay. Let everybody take a look at that and make sure they're okay with it. Are there any questions on that example? Again, what is this all about? If you've lost track of kind of what is all this about, remember, we're just practicing how to find eigenvalues and eigenvectors of a matrix. And Edgar has an incredibly good question in the chat. So it's so good that I'm not going to answer it until I erase this board fully. I want to get totally focused in on it. I was wondering if anybody was going to notice that the eigenvalue that repeated twice, which was lambda equals 2, ended up giving me a 2-dimensional eigenspace. 2 eigenvectors in that basis, whereas the other eigenvalue, which was lambda equals 4, that only shows up once and gave me 1 eigenvector. So the natural conjecture, the natural conjecture at this point would be, is it true, Dr. Hannon, that the number of repeats of the eigenvalue is always going to dictate how many corresponding eigenvectors we get? It's true in this example, but it turns out it's not always true. And our next example is going to show us that. However, when this is true, when Edgar's observation is correct, our matrix is super good. Our matrix is going to be called diagonalizable. I'm going to define that word for you in just a few minutes. But before I do that, I just want to show you another example. I want to put your curiosity to rest and show you that no, it is not always true that every eigenvalue will always pull its weight. Right? You can think of it that way. The weight of this eigenvalue is 2. It shows up twice as a root of the characteristic equation. And in this case, that eigenvalue did pull its weight. It gave me 2 eigenvectors in this basis. And so together, if I look at all of the eigenvalues together, we got 3 basis vectors. Actually, that would be a basis for Rn, for R3 in this case. This vector, and this vector, if you take all 3 of them together, that's 3 basis vectors for R3, as it turns out. So that's a good thing. That's actually something we want to tap into a little bit more. Okay, I'm getting ahead of myself because I'm excited. But in fact, we really should, unfortunately, we're going to find out in this next example, which is example 3, we're going to find out that this is not always the case. And so the answer to Edgar's question is actually going to be no. It's not always going to work out this way. And so here's the example. Find bases for the eigenspaces of, I'm going to make a matrix C here. And the matrix C is going to be 3, 0, 0. And then 0, 2, negative 1, and then 1, negative 1, and 2. So this time I'm going to call the matrix C, so we don't confuse it with the other 2 examples. And what we want to do is the same thing one more time. I want to try to find the eigenspaces of this matrix. And so for the solution, again, we're going to take the determinant of what we get when we subtract lambda off of the main diagonal. So again, I'm going to do that here. The determinant of this matrix that I'm writing down. And I've been subtracting lambda off of the main diagonal of it right here. And can somebody suggest how to figure out this determinant or how to simplify this determinant? Anybody have an idea for me? Yeah, Tien's got it in the chat. In this case, if we look at the first row of this matrix, notice there's a lot of zeros in that first row. And we can use that to expand this determinant. So I'm going to expand, I'll just put it right here if you don't mind. I'm going to expand row 1. And so if I do that, I'll have 3 minus lambda. And I cross off that row and column, and then I get 2 minus lambda times 2 minus lambda, and then a minus 1 in brackets here. Again, I do not want to multiply this all the way out. If I multiply this all the way out, I will end up with a cubic equation that I don't know how to factor. My goal is to get it factored. And if I look at what I have right now, it's already partially factored. Right? The 3 minus lambda is factored out already. And the rest of it, which I'm going to put in these brackets, is just a quadratic. It's just a quadratic. So I'm going to get lambda squared minus 4 lambda, and then plus 4 and minus 1 is actually plus 3. So I'm doing this kind of quickly, guys. It's just the algebra of simplifying the quadratic that's in those brackets. But there's nothing terribly exciting going on here. I'm just trying to get this thing factored. The part in brackets will factor as lambda minus 3 times lambda minus 1. And I'm going to set that equal to 0 again. To find the eigenvalues, I have to set my characteristic equation equal to 0. And look at what you have here, guys. Lambda equals 3, 3, and 1. 3, 3, and 1. That's the idea. Okay, let me come over here. While I'm erasing this board, which is a little bit tenuous, check the fun facts for me. Let's make sure those lambdas are correct. Check the trace and the determinant and see if these lambda values are compatible with that. Okay, let's take a look here, gang. Right, the trace of this matrix, 3 plus 2 plus 2, that's 7. If I add up my lambdas down here, 3 plus 3 plus 1, yep, that adds up to 7. If you do the determinant of this matrix, again, you can expand the first row of it, for example. The determinant of this matrix is going to be 9. And if I multiply my lambdas together, again, I have to count the repeats. If I multiply those together, I also get 9. Okay, so let's start off by looking at lambda equals 3, because that's the eigenvalue that was repeating. And I generally recommend that we focus on that eigenvalue first. I'm going to have a null space to look at. Let's write it down. If I subtract 3 from the main diagonal of the original matrix C, so I'm just going to subtract 3 from everything. If I do that, this is what I end up with. The first row is all zeros. The second row is 0, -1, and -1. And the third row is 1 and -1 and -1. And if I wanted here, I guess I'll do it. You can permute the bottom row to the top. So I'm just doing a quick ERO here, although you can probably figure this out in your head as well. The row of all zeros, I could move that to the bottom. I could take out the minus sign on the middle row and then put the bottom row at the top, something like that. But guys, if you look at this, so here are my variables, x, y, and z. If you look at this, if we let z equal t, that's actually the only free variable. So we could let z equal t. If we do that, then when we solve for y, y is going to be equal to -t. And then from there, we can quickly solve for x. X will turn out to be equal to 0. And so if I bust out my variable and write down my basis here, my basis for this eigenspace corresponding to lambda equals 3, when I bust out that t, I will get 0, -1, and 1. Look at that, guys. Look at that. That is interesting. That is interesting. This is the eigenvalue that was repeated twice. And so Edgar's question in the chat was, if the eigenvalue was repeated, would it give you 2 vectors? And here we see that even though the lambda equals 3 did repeat twice as a root of the characteristic equation, it only gave me 1 vector. It did not pull its weight. It's a difference between this matrix and the previous one. And I'm going to talk about that in just a minute. But anyway, so this matrix is somehow defective. This eigenvalue, lambda equals 3, did not pull its weight. Okay, I'll put some notes in. I'm going to write this down in the notes for you in a minute. But I just wanted to finish that off. Now, there is another eigenvalue here, which is lambda equals 1. And I'm going to let you guys check this one. So instead of doing a whole other null space again, I will let you guys check this because this gets a little bit tedious to keep doing these null spaces. So when you do lambda equals 1, I will just ask you to take my word for it for now that the vector 0, 1, 1 works as an eigenvector. Okay, so you can check that. I'll let you check that that actually is correct. Okay. So does everybody see the difference between this example and the previous one? In this example, both of these examples had an eigenvalue that was repeated. Both of them had an eigenvalue that was repeated. But on matrix B that we did in the previous example, the repeated eigenvalue gave us 2 eigenvectors in its basis. In this example, the eigenvalue that was repeated, which is lambda equals 3, only gave us one eigenvector. And because of that, we only get a total of 2 eigenvectors here. One for the first eigenvalue and one for the other eigenvalue. We don't get 3 of them like we did with the previous matrix. So this leads us to a definition. And I want to put this into the notes now. This turns out to be an extremely important thing that we're going to be talking about. An n by n matrix. An n by n matrix, I guess I'll call it A again. An n by n matrix A is called non-defective. Non-defective, or there's another word that's interchangeable with that. So, or we could also call it diagonalizable. So it's kind of a fancy math word. Diagonalizable. So it's called non-defective or diagonalizable if A has n, if A has n linearly independent eigenvectors. Okay, so if the matrix has n linearly independent eigenvectors, otherwise A is defective. Otherwise, A is defective. So every matrix will either be defective or non-defective, depending on whether it has n linearly independent eigenvectors. Give myself a little more room here. So that's an important definition that we want to study a little bit in this chapter. I have to tell you something. When I was a student learning this stuff, I got confused because I was like, well, what's the difference between diagonalizable and non-defective? It turns out there is no difference at all. And I think that's why I was confused. We have 2 different words that mean the exact same thing. So if I say non-defective, it's the same thing as saying diagonalizable. They are exactly interchangeable words. And so there's no need to worry too much about that. So I'm going to do something very bold and brave here. I'm going to try to pick up my phone for a minute and walk you over to a board where I tried before class to, let's see if you can see this. I tried to write down on this board a summary of the 3 matrices that we looked at earlier. Can you guys all see that? Is it reasonably visible? So I just want to ask, which of these matrices is non-defective? Right? So remember that the very first example that we did today, which was the matrix A, that was only 2 by 2. So the first matrix A was 2 by 2, and so this is already in your notes. But because it was 2 by 2, notice that it does give me 2 eigenvectors. It had 2 linearly independent eigenvectors right here and here. Okay. The matrix B was a 3 by 3 matrix, and look at that. We did get 3 eigenvectors. Okay, everybody pulled their weight. But matrix C, which was also a 3 by 3 matrix, only gave us 2 eigenvectors in total. And so that matrix turns out that matrix is defective. We don't get n linearly independent eigenvectors. So maybe we should write that into our notes here. Let's come back to the main board so that I can write that down for you. The point is, so in the examples above, A and B are non-defective, but C is defective. So the first two examples were non-defective, but the third one was defective. Okay. Now, to help us talk about this a little bit, I'm just going to say a couple more words about this, and then we'll do one more example, and then we'll be pretty much done with the new material for today. I want to make a quick little notation to help us talk about this. And the notation is the following. For each eigenvalue lambda, I'm going to let m sub lambda denote the what's called multiplicity I'm going to denote with m sub lambda the multiplicity, or in other words, the quote unquote weight of lambda. Right? So in other words, m sub lambda, if you want to just put it in layman's terms here, m sub lambda is simply the number of times lambda repeats in the characteristic equation. Okay, so m sub lambda, that's called the multiplicity of lambda. That is the number of times that lambda repeats in the characteristic equation. And so in that case, I can make a little remark to re-express what non-defective means. So let me just come back over here. Right, so then just as a quick remark that kind of uses this notation, right? Here's a quick remark for you guys. The remark would be the following remark. Namely, if we look at A, which is some n by n matrix, this matrix A is non-defective if and only if. I'm going to give you another way of thinking about it. Non-defective. A is non-defective if and only if, and now here is another way of thinking about it. The way I'm going to say it in words is that every eigenvalue lambda, quote unquote, pulls its weight. Every eigenvalue pulls its weight. That's what non-defective means. In other words, I'll say it one more different way. Now I'm going to use the multiplicity notation. In other words, another way of saying it is that the dimension of each eigenspace E sub lambda should be equal to the multiplicity of that lambda. So, that might, yeah, I think you can read that. The dimension of the eigenspace matches the eigenvalue's multiplicity for each lambda. So these are nice ways of thinking about what non-defective means. The definition is still here, namely that we have to have n eigenvectors produced by these different eigenvalues. But how are we supposed to produce those n eigenvectors? Well, each of our eigenvalues is supposed to produce eigenvectors for us. By the way, every eigenvalue will produce at least one eigenvector. You can't have an eigenvalue without an eigenvector. But when you have an eigenvalue with a larger multiplicity, if m sub lambda is larger, so if the number of repeats of the eigenvalue is, say, more than 1, then the number of eigenvectors that you obtain, which is the dimension of the eigenspace, needs to match it. Needs to match it. That's what this remark is saying. And that did not happen with matrix C. The third example that we just did a few minutes ago, we had an eigenvalue of multiplicity 2 that only produced one eigenvector. It did not pull its weight, if that makes sense. You guys with me? Now, I know what some of you might be thinking out there. Some of you might be thinking, well, Dr. Annan, if one of the eigenvalues doesn't pull its weight, maybe one of the other eigenvalues could overpull its weight and make up for that. Like, would that be possible? That would be a question that might get asked. Somebody might ask, well, if one of the eigenvalues falls short and does not pull its weight, could you make up for that by producing an overabundance of eigenvectors for a different eigenvalue so that at the end of the day, you had n of them, like the definition requires? The answer is, and you'll learn this in Math 307, that could never happen. No eigenvalue will ever be able to overpull its weight. Meaning that if there's even one eigenvalue that is not pulling its weight, then it's game over. The matrix is going to be defective. You will not be able to make up for a shortfall that one eigenvalue produces by overpulling the weight of another eigenvalue. It's not going to happen. That's what I'm trying to say. Does that make a little bit of sense? Okay, so we've got 3 good examples so far today. If you don't mind, well, actually, we could take a break. I have one more example I want to do, but we can take a break now and then come back to that. During this 10-minute break, guys, I've noticed not very many people have turned in the homework yet that's due tonight. If you have questions on the homework for tonight, just throw them into the chat. Send the note to everyone. Don't send it to my private don't send it privately to me, send it to everyone. From 6.4 or from 7.1, if you would like me to go over any of the homework that's due at midnight tonight, during the break, you can put those in the chat for me. But let's take 10 minutes and then we'll come back and do one more example of this, and then I'll take some homework questions. Sound okay? All right, see you guys in a few. Guys, if you're out there within the sound of my voice, in about 1 more minute, I am going to get started again. So this is not a bad time to find your way back over to your screen. We'll take another minute here and make sure everybody has a chance to get back in front of me here. Well, we have a lot of homework problems. That's okay. The challenge will be if I can figure out what the questions are asking. If anybody happens to have their book in front of them and could take a picture of the problems from 6.4 or 7.1 and throw them into the chat, that would definitely help me out in terms of making sure I know it. I mean, I'm trying to figure out what the questions are. Most people don't write down the questions when they turn in the homework, so it's hard for me to figure them out. I have an old version of my book here, so I roughly know what these questions are. But as I said, I came back here not anticipating. I didn't anticipate that I was going to be over here, so I did not bring my book with me. So it's a little tricky, but I would love it if anybody does have those. You could put those in the chat because I might be able to get them from the chat as well. So anyway, I think I'm going to go ahead and get started again, though, in the meantime. Before I start into looking at some of those homework problems, yeah, thanks, Fook. I appreciate that. Those are going to be helpful for me to look at. I wanted to make a couple of final comments about what we just talked about tonight and then do one last example. Okay, so that's what I'm going to do here first. I first wanted to make a remark about the remark that I kept up on my board over here. So as you can see, whoops, you can't see it if it falls over. As you can see, the way I like to think about non-defective matrices is they are matrices where every eigenvalue pulls its weight, okay? And another way to rephrase that is that the dimension of each eigenspace matches exactly the multiplicity of each eigenvalue. So if all of the eigenvalues pull their weight and they have the same multiplicity as the dimension of the eigenspace that they create, then our matrix is non-defective. So just as a quick remark, I sort of said this briefly, but I didn't write it down. If the matrix has no repeating eigenvalues, so if all of the eigenvalues are distinct, let's write this here. If all eigenvalues of A are distinct means no repeats, right? So there's no repeats. No repeat lambdas. So if none of those lambdas repeat, then A will be non-defective, for sure. Then A is guaranteed to be non-defective in that case. That's because every eigenvalue will always pull its weight if its weight is only 1. So every eigenvalue, guys, right? Every eigenvalue will always produce at least one eigenvector. You can't have an eigenvalue without an eigenvector. So as long as there's no repeats, you're guaranteed to have a non-defective matrix. If the matrix does have repeat lambdas, then it's a maybe. Then it's a maybe, and we've seen examples both ways tonight, haven't we? Right, the matrix B and the matrix C that we looked at earlier, which should be in your notes already. I know it's not on the board here, but in your notes earlier, we had the matrix examples of B and C, and they both had repeat eigenvalues, but B was non-defective while C was defective. So it depends on whether the eigenvalues pull their weight. So my advice here my advice, I guess I could even write this as advice. My advice is check the repeat lambdas first. If somebody gives you a matrix and they ask you, is it defective or non-defective? It's a natural question. I'll probably ask you that question 50 times between now and the end of the semester. I give you a matrix. I say, is it defective or non-defective? You're going to need to find the eigenvalues. And if there are repeat lambdas, if there are lambdas that showed up more than once, in other words, with a multiplicity of more than one, then those are the lambdas that you need to check. You need to make sure that they pull their weight. Right. So just wanted to give you that advice and kind of just this little remark here. If your matrix does not, there's a couple problems on, I think, the homework for Friday where the matrix, they give you a matrix and they say, is it defective or not? And you look at it and say, oh, there's no repeated eigenvalues. Then you're already done. If you know that there's no repeated eigenvalues, you don't even have to find the null spaces. You don't have to do all that hard work. You can skip it. You can just say, look, if there's no repeat lambdas, the matrix is guaranteed to be non-defective because every eigenvalue will pull its weight of 1. Okay, hopefully that makes sense. I just wanted to throw that in as a little afterthought during the break. I was thinking about that, and I thought that might be helpful. Okay, I want to do one more example tonight, guys, before we get to looking at the homework. Let's take a look at this one that's right here. I would like to find the bases for the eigenspaces of this matrix D, and I'm going back to a 2x2 here. All right, so let's do it. I'm going to try to write the solution here. As always, we're going to start with the characteristic equation, which means I need to subtract lambda off of the main diagonal. So I get 2 minus lambda and then negative 13. And then on the second row, I get a 1 and a 6 minus lambda. If we just use our little 2x2 formula, I don't mind using that formula for a 2x2 matrix. We'll end up with 2 minus lambda times 6 minus lambda plus 13. And if we just expand that all the way out, you can see that we would have lambda squared minus 8 lambda plus 25. And this is the characteristic equation that we're going to set now equal to 0. I'm going to set that one equal to 0. So this is a quadratic equation, right, guys? Not too bad. However, what you're going to notice about it pretty quickly in the analysis here, it does not factor nicely. It will factor. It will factor. It's just it won't have nice solutions. It doesn't factor cleanly, nicely using whole numbers like all of the earlier examples that we did. So what are we going to do in this kind of a situation where I don't have a nice factorization that I can just bust it down? Well, if it's a quadratic equation, I know that I can always fall back on the quadratic formula. And that is what I'm going to do here. I'm going to use the quadratic formula. I hope everybody remembers it, right? So it's going to be lambda equals the negative of b, which is 8, plus or minus the square root of b squared, which is 64, minus 4ac, which is 100, all divided by 2. And I'm just going to make that a little nicer. 8 divided by 2 is 4. And then look what we have under this radical, guys. This is the square root of 64 minus 100. 64 minus 100 is actually negative 36. What is the square root of negative 36? Bond's got something in the chat. Let me see. 6i, that's it. Yeah, that's it. Thank you, Stephen. Yep, that's right. 6i. It's imaginary. It's 6i, and then of course by the time I divide that by 2, it's going to be 3i. So guys, these are your lambdas. Your lambdas are 4 plus 3i and 4 minus 3i. And by the way, those lambdas will still satisfy the fun facts. So if you add them up, if you take 4 plus 3i and you add that to 4 minus 3i, you add up those lambdas, you're going to get 8. And yep, that's exactly the main diagonal of the matrix. So the fun facts are still true, but we don't have very nice eigenvalues here. They are imaginary. So I want to talk about how we're going to handle this, because this is going to come up. This can come up in the real world, and we got to be able to deal with it. So what are we going to do? Well, let's take a look at the first eigenvalue, which is 4 plus 3i. Let's take 4 plus 3i. As usual, I have to do my little null space thing. So let's just remember, how do we make this matrix? The way we make the matrix is we subtract the eigenvalues off of the main diagonal. Get this out of the way here. So we're going to subtract 4 plus 3i from the main diagonal of D. So that's going to actually give me -2 minus 3i. And then we have -13. And then we have 1. And then we have 2 minus 3i. So the imaginary number starts to infiltrate the matrix. Yeah. So here is where we really have to trust the theory. You know what? As soon as imaginary numbers start showing up in this matrix, it hides the fact that these two rows have to be multiples of each other. You remember the matrix, the first matrix tonight, where we had like 6, 6, and then 9, 9? It was really obvious. It was super obvious that the second row was just a multiple of the first row. Here, it's not nearly as obvious, but you know what? It has to be true. It's just that the imaginary numbers sort of camouflage that. They make it less obvious, but it turns out that you can take this first row and multiply it through by a scalar and get the second row. So we are going to trust the theory, and we're going to trust the fact that we have to be able to cross off a row or to zero out a row. It has to happen. Remember, this matrix is not invertible. So it has to be possible to cross off a row, leaving me with just one pivot. And now, okay, so we got rid of that row. And now you can see why maybe I don't want to deal with the free variables thing. Do you remember my A-B trick from just a few minutes ago? It is especially helpful when there are complex numbers around. So I'm going to remember my A-B trick here and go straight to my basis. My basis for E sub lambda equals 4 plus 3i. So if I take that particular eigenvalue and I want to write down my basis, I can go straight to it. How do I do it? I switch the order of the A and the B, and I do a sign change on either the A or the B. It doesn't actually matter which one. So I'm going to put the B first, I'm going to put the A second, and I chose to put a minus on the A value. So the A, I chose to write the A as a -1 here. Is that all visible? Yeah, okay. So there you go. Notice I didn't have to break a sweat. I didn't have to do any EROs. I didn't have to set up any free variables. These are tricks that you guys are lucky. I've taught the class 40 times. The first time I taught the class, I was making everybody struggle with all the EROs and the free variables and stuff. It's a lot more of a headache than what we have here, right? Oh, by the way, I forgot to mention something. This matrix, do you see? See my remark before I erase it? If all of the eigenvalues are distinct, then A will be non-defective. Do you notice over here, are there any repeated lambda values in this example that we're doing right now? No. 4 plus 3i is not the same as 4 minus 3i. There are no repeats. So I could have said right here, I could have even said before I even started looking at the null spaces, I already knew that this matrix was non-defective. Non-defective in this case. Okay, there is also another eigenvalue for this example. There is another eigenvalue for this example. Do I want to do it? Yeah, so I'm going to make a quick another little remark here, guys. I'll write it down real quickly, and then we'll realize here that we also don't have to do we don't have to do any work for the other eigenvalue either. So what this remark says, and I'm not going to prove it, but what it says is that if A has a complex eigenvalue, if A has a complex eigenvalue, let's say lambda equals A plus BI, with eigenvector V, which would be also complex, so it might be R plus SI. So that's actually what we have here, guys. This can be thought of as this is like 2, -1 plus -3, 0 times I. So you can think of this vector if you kind of bust out the real part that does not have the I on it, and then the part that does have the I on it, kind of separate them out. This is like the R and the S that I'm talking about here. So if you create an eigenvalue eigenvector pair, like what I've done here so far with the first lambda value, then it turns out that the other eigenvalue, which is often called the conjugate of lambda, so this is written with a bar on top of it, and this would be the eigenvalue A minus BI, and this is also an eigenvalue. And with the corresponding eigenvector, so this is also an eigenvalue with eigenvector, and here, be careful how you write this, guys. We're going to conjugate the vector V. So I've got a bar and an arrow on that V right there. Okay, and so what this is this is R minus SI. So it turns out that you can write down the other eigenvector without having to do a whole nother null space. So this remark just says once you've struggled and toiled away with one of the eigenvalue eigenvector pairs, then for any complex conjugate pairs, you can just write them down. And so in this case, we can do that. Lambda equals 4 minus 3i. Let's go back to our example here. 4 minus 3i. What is the corresponding, let's write it down as a basis. I can go straight to the basis here. We can go straight to the basis. I'm just going to say basis because I'm running out of room here. But the basis will just be 2 plus 3i and -1. Okay, so I don't have to calculate anything. I can simply take the work. I can take the work that is on the top of my board. I can take that vector and I can, notice what I did. I switched the signs of the I parts only. See how that works? The R plus SI turns into R minus SI. So here, anything that was without an I in front of it is the same. But if there was a I term, like the minus 3i, it turns into plus 3i. So that's kind of interesting. You can just write that down immediately without having to do another null space. Again, that's just a trick. It's just a trick. If you wanted to find the other null space and work it all out from scratch, you certainly can do that, but you won't get anything interesting other than just the same answer that I just described. Okay? Any questions about that, guys? Okay. I tell you what, I'm going to take the 3 minutes that I have and start working on the homework. I see there's quite a few questions here. So let me see if I can start working on some of the questions that you guys have put in the chat. We're going to leave it at this for now in terms of the material. On Thursday, I'm going to talk about why a non-defective matrix is a good thing. And Antonio, yes, all of this is true for larger matrices as well. Absolutely true. So if you don't mind, I'm going to take just a couple minutes and try and do a couple of the problems from the homework. I want to do number 43 from section 6.4, if I could. I'll at least try and do that. And then we'll see how far I get. I might end up having to, maybe I'll make a video or something with some of the other ones. I did get this question sent to me, so I can go ahead and help you with it right now. 43 says, now we're switching gears completely. I'm going to talk about linear transformations for just a few minutes. If we have a transformation from V to W that is 1-to-1, then in that situation, if we start off with V1, V2, all the way up to V sub K is Li, then the question is asking us to prove that if we take the set of T of V1, T of V2, and T of Vk, that this is still Li. So this is a theoretical problem, and it's one of my favorites. I really like this question, so I wanted to make sure to do it. To show that a set of vectors is Li, I'm going to just cut to the chase because I'm kind of running short on time. I'm going to assume that I have a linear combination of these vectors that cancels out. So let's just say C1 times T of V1 plus C2 times T of V2 plus dot, 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 plus Ck times T of Vk equals 0. So this is a problem that forces us to remember what linear independence means, or what the definition of it is. So that's kind of a review back to chapter 4. And the idea is that for linearly independent vectors, you have to show that if you cancel them out in a linear combination, like I'm assuming here, you might remember from a few weeks ago that what linear independence would require is that all of the constants are 0. Right, so I would like to prove that all of the constants are 0 from these assumptions. My assumptions are that the original vectors are Li and that the transformation is 1-to-1. Okay, well, the first step here, guys, is to remember that when T is linear, it has to respect addition and scalar multiplication. So I'll just say, since T is linear, I can stuff all of the vectors and constants inside. I can stuff it all onto the inside. So I can put everything on the inside right here. That's because T respects that linear combination. Okay, and this means, does anybody remember, what does it mean when you transform a vector and it becomes 0? Does that ring a bell? That actually means that the vector that was being transformed, this is a good review from before spring break, that vector is in the kernel of T. It's actually in the kernel of T. So the kernel of T, those were the vectors that get transformed to 0. But since T is 1-to-1, I'm going to go kind of quick on this, guys. Since T is 1-to-1, that just means that the kernel of T is 0. Definition of 1-to-1 is that the kernel of the transformation is 0, and so C1 V1 plus C2 V2 plus dot 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 plus CK VK, all of that is 0. And now, last step, guys, and then we're done for today. We have a linear combination of the original vectors that's canceling out. And so that means that all of the constants are 0. So since the original V1, V2, and so on, those original vectors are Li, then the definition of that is that all of the constants are 0. They're all going to be 0. And so T is 1 to 1. Awesome. Okay. Does that make sense to everybody? It was a little quick, I know. All right, well, I am kind of out of time. So what I'm going to do, I'm going to write down a few of these other problems that people had put in the chat. And I'm going to make another video for you, like I did last time. I'm going to do it after my second class, and then I'll send it out. Does that sound fair?
Yes.
Okay, yeah, sorry, I always run out of time. 15, 19. Okay, so with that, guys, I think I'm going to go ahead and call it a day for now. Thank you so much for being here. Again, apologize for all this Zoom. I'm going to try, Joe, I'm going to try and solve the problems that were put into the chat, some of them anyway. There's quite a few of them there. I may not get to all of them, but I'll pick some of them, okay? And once I send out the video, I'll tell you which problems are in the video. All right, guys, thank you so much for being here. I will look forward to seeing you again on Thursday. We're going to be in Zoom one more time. Thanks so much. Bye for now.